So, for the final session, we're going to have Jennifer talk about practical implementation, part 2.
Can you hear me? Okay.
Pardon?
I must apologize because Chris and I at the beginning of today's session didn't break down our talks into different sections to let you know ahead of time what we would be talking about. So the practical implementation of NAVA Part 1 was actually focusing on invasive NAVA studies, and my talk will focus on the practical implementation of non-invasive NAVA. So just my apologies for that. This is a video, we've been showing it for a few years now. It shows a healthy subject who has the catheter down, and there are electrodes on this catheter picking up her diaphragm electrical activity. The electrical signals are being sent to the ventilator, which you'll see here. This was a research prototype that we had, I believe, in 1998. And as Art was mentioning before, there is no connection between the patient and the ventilator to control it. So it's the electrical activity of the diaphragm that is controlling the ventilator, which is inflating this lung model. Okay? These white bands she has around her chest have nothing to do with NAVA. It's part of a research study we were doing. But you can clearly see with the movement of her chest and the inflation of the lung model that there is synchrony in a situation where you have 100% leak. Okay, so the idea of using an electrical signal to control the ventilator opens up a whole new field of possibilities for non-invasive ventilation. So I think we've seen the size does not matter joke at least a few times, but it's true. This is the same type of a video in a 350-gram rat. So this is an anesthetized rat who is spontaneously breathing. The rat has the catheter down through the mouth. It's picking up the diaphragm electrical activity. This signal is being sent to the ventilator, and it's inflating this lung model here. And you can see here, as we've indicated, the tidal volume is around 2 ml. So in very, very small species as well, you can do non-invasive synchronized mechanical ventilation. So you can see here the inflation of the lung model in synchrony with the very, very small displacement of the chest of the rat. Again, it's in the presence of a 100% leak. I don't know if you're familiar at all with the helmet device. It's another type of a non-invasive interface. I think Bob showed some pictures of it today. And what I'm showing you here is a healthy subject who is breathing on NAVA with the helmet interface. And normally this is a device that's very hard to synchronize because it is so large and to detect any kind of flow or pressure changes for triggering. And you can see here on the bottom tracing, we have the diaphragm activity. On the top, it's not that easily seen, but you have the airway pressure or the pressure being delivered, and you have here the esophageal pressure. So in this healthy subject, we were actually able to 100% unload with NAVA with this non-invasive device. That's just a few videos. The next few slides I'm going to show you are from studies that were done by fellows who are visiting us in our lab. I am not the principal investigator, and hopefully I will do justice to them. We did a study 2 years ago where we compared flow triggering and neural triggering of the helmet device. So the mode is pressure support, and all we've done is we've changed the trigger signal. On the top panels, you have the diaphragm electrical activity, the airway opening pressure, which is the pressure that we measured in the circuit just before going into the helmet, the esophageal pressure, and the gastric pressure. And on the left, it shows you the tracings that were obtained when we used flow triggering. And then on the right side panel, we have when neural triggering was applied. So The main point is during the flow triggering, you see that there is asynchrony where you have, first of all, delays where the diaphragm activity was starting, and then you have a delay before the ventilator reacts and triggers to deliver the assist. You also see that every second breath in this case is a wasted effort. So here you have an inspiratory effort made by the subject. These are healthy subjects, by the way, where the ventilator failed to trigger. Here you see there's a wasted effort. And then what we did was when we switched over to the neural trigger, where the diaphragm electrical activity, when it begins to increase, sends a signal to the ventilator to start delivering the assist, and you use the diaphragm activity to cycle off the assist as well, you see that we were able to restore the synchrony with this device, which is normally difficult to synchronize. This slide shows for the group of healthy subjects the inspiratory and the expiratory delays when subjects were breathing at different pressure support levels, 5, 10, and 15, and at different respiratory rates of 10, 20, and 30. And the pale gray bars represent the when we were using the neural triggering, and the dark bars represent when we were using the pressure triggering. Sorry, the previous thing is we were using pressure triggering in these helmet thing. And what you can see here is that independent of what pressure support level you use or what respiratory rate, that the inspiratory delay, so the time between the time that the diaphragm begins to be active to the time that the ventilator starts giving the assist, the inspiratory delays are reduced when you use a neural trigger. And it's even more striking, as Christer showed in his previous slide, that the expiratory delays, when you cycle off with the neural activity, are also much shorter with the neurally controlled interface. And what is the impact of this? And what we did was we also rated subject comfort. And what you can see here again is the subject comfort from 0 to 10, 10 being the most discomfort, I believe, and 0 being very comfortable. And you can see here that when the pressure trigger was used compared to the neural trigger, independent of what pressure support level you were using, maybe here there was equal comfort, but in general that the neural triggering was giving more comfort. Because we get asked very often, what is the impact of the asynchrony, or does it make you more uncomfortable? Well, in this study, we found that when you were more synchronized, the healthy subjects were more comfortable. I'm going to switch a little bit to the animals again. We did a study where we were looking at implementing NAVA before and after extubation in an animal model of lung injury when the animal was in severe hypoxemic respiratory failure. And the only way I can explain to you the protocol is to take you through the different steps and show you the tracings. We have the rabbit who is initially orally intubated and having the diaphragm electrical activity measured with a catheter. So we'll start here on the left side, which shows the oral intubation. You have the diaphragm electrical activity and the airway pressure and the esophageal pressure that we measured while the animal is breathing on NAVA with a very high PEEP level. This was in order to eliminate the tonic activity I described to you before. We had to give a high PEEP to restore the phasic breathing. And again, a very sick animal. So then what we did was we removed the PEEP, and you can see here, if you look at the diaphragm electrical activity, that upon removal of the PEEP, there was an instantaneous increase in the tonic activity of the diaphragm. Okay? And then when we extubated, we placed an endotracheal tube 2 centimeters into one nostril of the rabbit, and we connected the ventilator to that. So the mouth was open and the other nostril was free. And you can see here to the right of the dashed line, when we were ventilating with NAVA using this single nasal prong, that there was the tonic activity disappeared completely. This is on a low level of NAVA, so the diaphragm electrical activity is very strong, as you can see here. Okay, there's no NAVA being delivered, and the esophageal pressure swings are very large, indicating a large work of breathing. Then what we did was we increased the NAVA level a little bit, and we saw after a few breaths that the diaphragm electrical activity went down, so the respiratory drive decreased. Still, we see no tonic activity. The assist is being delivered in synchrony and in proportion to the diaphragm electrical activity. And I need to remind you again, this is with one single nasal prong. It's inserted into the nostril. You can hear shh, leaks going all the time. And then again, when we increase the NAVA level 4 times, we receive these pressures, which is about peak pressures of about 40 centimeters of water. But we are able to unload the respiratory muscles. And we're able to unload the respiratory muscles by giving synchronized, non-invasive, positive pressure ventilation. And what's interesting about the extubation here is when we removed the PEEP and the tonic activity increased, when we remove the tube, what in fact we're doing is we're actually liberating the upper airways, and now the muscles of the upper airways can participate in regulating FRC, and they can relieve the diaphragm from all that tonic activity. So you can start to see that we didn't actually measure these muscles, but we can hypothesize that they start to play a role in maintaining the FRC, allowing the diaphragm to concentrate more on the phasic component. This is the data on unloading during this non-invasive NAVA study we did. You have the diaphragm electrical activity on the y-axis and the esophageal pressure. So the diaphragm electrical activity are the black solid symbols, the esophageal pressure are the empty ones. What we've done is we've plotted these values as 100%, because what we did, we took the animal off the ventilator completely to get the maximum diaphragm activity and the maximum esophageal pressure swings. So we called that 100%, and then what we did was, as we progressively increase the NAVA level, you can see that the diaphragm electrical activity and the esophageal pressure are progressively going down, indicating that we're actually achieving respiratory muscle unloading. You can see here the mean ventilator delivered pressures, the group mean values, and you can see here that we were actually able to achieve the same amount of diaphragm electrical activity and esophageal pressure swings as we observed before the lung injury. So this is the first mode of ventilation, at least, that can provide synchronized respiratory muscle unloading. I think that the neonatologists will be very happy to see this graph. It shows you what the baseline gastric pressure was during these non-invasive runs. On the x-axis is the mean level of the assist delivered when we are progressively increasing the NAVA level, and it, at least in the rabbits and in this model, there doesn't seem to be any evidence that we're inflating the stomach. Okay, there seems to be a big problem with CPAP belly and things like that, and even when we were giving peak pressures of 40 centimeters of water, we didn't see any effect on gastric distension. I was fortunate enough to be working with Lucas Brander, who is an expert in measuring hemodynamics in rabbits. So during this study, we also measured the cardiac output and pulmonary artery pressure. And on the top panel, you have the tonic diaphragm electrical activity, just to show the impact of the PEEP on the diaphragm electrical activity and the hemodynamics. And as I showed you in the raw tracings before, when you're intubated after the lung injury with a high level of PEEP, we're trying to minimize this tonic electrical activity of the diaphragm. For the group, when we removed the PEEP, there was a huge increase in the, like a doubling of the tonic activity. And then after extubation, still with no PEEP applied, the tonic activity of the diaphragm went down for the group. And you can see here that, of course, as we all know, when you remove PEEP, there's an improvement in the cardiac output and a reduction in the pulmonary artery pressure. But what's nice is that if you're able to do non-invasive positive pressure ventilation and you allow the upper airways to keep the PEEP, let's say, that you wouldn't have this impact on the hemodynamics. This is a slide that I like to show and to tell you to take home. And if you remember anything from these lectures, I hope you remember this slide. It shows a rabbit who is breathing on pressure support with this single nasal prong, as I showed you. This is the diaphragm activity. This is the ventilator-delivered pressure. And these are the esophageal pressure swings. Of course, with such a huge leak, the animal couldn't trigger pressure support at all. After a few minutes, the PO2 went down, CO2 was rising, and what we simply did here was we flipped the switch on our prototype, which allows you to switch between modes. And this is an instantaneous, like a continuous recording, and you can see here when we switched right away to NAVA that you were able to deliver synchronized, non-invasive, positive pressure ventilation, and there was an immediate reduction in the work of breathing and the diaphragm activity, and after a few minutes the blood gases improved. So if you remember anything from these lectures, I think that this is a very nice slide to remember. So I think this is going to be the first time that I'm going to speak on behalf of Krista and I. I'd like to summarize our talks by telling you what our goals are with using NAVA. And so of course, the first goal that we have is that we would like to improve patient-ventilator interaction. By doing this, we might be able to reduce the work of breathing. We might be able to provide an improved ventilation, but also maybe a safer ventilation. Again, we don't know. We have to do some outcome studies. If you have improved synchrony, you have less fighting the ventilator, you might be able to reduce sedation or paralysis. As Krista showed you, that the NAVA responds to changes in drive. So if you have a change in your metabolic demand, like for example a fever, that NAVA would respond to this over time. We showed you that with NAVA, you're forced to use your diaphragm electrical activity. Therefore, this might prevent disuse atrophy of the diaphragm. It's believed maybe that this could shorten weaning time. We don't know. We have to study that. And I'm a firm believer that we can definitely improve non-invasive ventilation with this mode. And I just want to also end by thanking this guy here in the bottom left. You've seen him in all the videos. He's put down the catheter at least 3,000 times, Norm. He's sitting in the back. All he asks for are chocolate chip muffins and a can of V8 every time he does it. So I just want you to know he's always there for us, morning, noon, and night. He has a wide job description, and I just want to say thanks, Norm. The two guys with the glasses are a programmer and the mathematician, and Sven, the guy on the left, is our programmer, and he's also there morning, noon, and night, and Lars was there in the very beginning when we were doing all the modeling and the electrode filtering and all that stuff. And on the right, you have the list of all the people, and I'm sure I forgot somebody, but also the family. Thank you very much.